Neptune looks like the next great destination, but it is really the place where human exploration starts breaking down. It is so far, so cold and so hostile that a mission there stops feeling like a round trip and starts feeling like exile. The deeper you look at Neptune, the more one fact becomes unavoidable. If anyone goes there, coming back to Earth may be the least believable part of the whole mission. The first thing that kills a mission to Neptune is time, not the cold, not the planet, not some dramatic accident. Time. Neptune is so far away that the mission starts breaking down on the calendar before it breaks down anywhere else. Neptune sits about 2.8 billion miles from the Sun, around 4.5 billion kilometers, roughly 30 times farther from the Sun than Earth is. That is not just a longer trip than Mars. It is a completely different scale. Real mission studies make that clear. Serious robotic concepts to Neptune take around 12 to 16 years just to get there, depending on the route and whether Jupiter is used to help bend the path outward. Another proposed mission to Triton, Neptune's largest moon, needed about 13 years for a brief flyby. That was for a robot. A robot does not need air, water, sleep, radiation protection, emergency medicine, or a way to come home alive. That is where the problem gets worse. The second you switch from a robotic mission to a crewed mission, every year starts multiplying the mission. More years means more food, more water, more spare parts, more shielding, more maintenance, more failure points, more chances for something small to turn into something fatal. A human Neptune mission is not just a ship with seats added to it. It becomes a moving life support system that has to survive for more than a decade before the hardest part of the mission even begins. And that raises a simple question. If the trip is already this long, how well do we even know the place people are supposed to reach? The answer is not reassuring. Humanity has barely explored Neptune at all. Voyager 2 is still the only spacecraft that has ever flown past it. Just one spacecraft, one pass, and only about 5.5 hours of close observation. That is the entire close-range record. In that short window, Voyager 2 still found new moons, new rings, and a giant storm system large enough to swallow Earth. That tells you Neptune is not a place we understand well and just have not visited recently. It is still a place that can surprise us in a matter of hours. That matters because a human return mission depends on knowledge. You need strong maps, reliable environmental models, good hazard data, good orbital data, strong timing predictions, and a clear picture of what can go wrong. Neptune is still missing a lot of that. Sending people there would mean building a round-trip mission to a planetary system that humanity has only seen up close once, and only briefly. So maybe the next thought is this. If robots can go, then eventually humans can go too. That sounds reasonable, until you look at the difference between robotic exploration and human survival. A robot can cruise through space for years with very little support. It does not need a pressure-stable habitat, it does not need oxygen, it does not need a doctor, it does not need exercise equipment to slow muscle and bone loss, it does not need psychological support, it does not need a protected place to hide during a radiation event, it does not need a second propulsion system reserved for the return home. A robot can also fail partially and still do useful science. A human mission cannot work like that. If the habitat fails, the crew dies. If the water system fails, the crew dies. If the medical situation goes beyond the ship's capacity, the crew dies. The engineering standard is completely different. That is why the real Neptune mission concepts people seriously study are still robotic. The serious plans are orbiters, probes and flybys, not crew cabins, not return ships, not long-term human operations. That is not because nobody has thought big enough. It is because the real engineering problem is already hard enough without adding biology. If the uncrewed version is still at the edge of what makes sense, then the crewed return version is not the next step. It is a leap into a much harder category. And time keeps making that category worse. Neptune missions are not only long on the way out, they are long in every phase. The ship has to work during a decade-plus cruise, then it has to work during arrival. Then it has to work during local operations in one of the least explored planetary systems in the solar system. Then it has to work again during the trip home. Every year adds wear. Every year adds uncertainty. Every year gives electronics more time to age, seals more time to weaken, software assumptions more time to drift out of date, and human bodies more time to decline. Then timing adds another layer. Outer solar system missions do not give you endless chances. Geometry matters, lighting matters, seasonal timing matters, some science opportunities disappear for decades or longer if you arrive at the wrong time. That means you do not just need a ship that can get there. You need one that gets there in the right era, under the right conditions, after surviving a huge trip without serious degradation. Missing a window is not a small delay when the target is Neptune. It can mean that the useful version of the mission is gone for the rest of a scientist's career, or longer. That is a very different way to think about exploration. Closer destinations still feel connected to human timescales. The Moon is close, Mars is hard, but still understandable in human planning terms. Neptune is where that starts to break. Neptune goes around the Sun once every 165 Earth years. That number matters because it tells you how slow the whole environment is. Seasons are massive, changes are slow, opportunities are spread across timescales that do not match a human life. A crewed return mission there would not feel like a fast expedition. It would feel like leaving one world behind and entering a place where everything important happens slowly except mission failure. And that is the first hard truth in this story. Neptune does not first destroy the mission with pressure, storms, or propulsion. It first destroys the idea that a mission like this can still behave like a normal round trip. The calendar starts pushing it towards something else, something heavier, something more fragile, something much closer to a one-way commitment than people want to admit. Then the next problem appears, and it is even more serious. Distance does not only stretch time, it also breaks communication, and once that happens, Earth stops being active support and starts becoming a delayed voice that is always too late. The next thing that breaks at Neptune is control. People hear mission control and assume that means somebody on Earth is still in charge and still watching, still ready to step in. Neptune, that stops being true. At that distance, light itself takes more than 4 hours to travel one way. That means if the crew sends a question to Earth and waits for an answer, the full loop takes roughly 8.3 hours even under good geometry. That is not a normal communication delay. That is the end of live support. No one on Earth is helping in real time. No one is talking the crew through a fire, a system fault, a bad burn, or a medical emergency while it's happening. By the time the answer comes back, the event is already over. It has either been solved locally, or it has already become a disaster. That changes the whole mission immediately. A Neptune crew is not operating with a support team in the usual sense. It is operating alone, with Earth acting more like a delayed library than an active partner. If a valve sticks, if a thruster fires wrong, if a life support loop starts drifting, if someone collapses, the crew does not get instant expertise from home. They get silence for hours, then advice that may already be outdated by the time it arrives. That is the point where mission control stops being control and becomes documentation. So the next question is simple. If Earth cannot respond in time, what does distance actually do to the mission? The answer is that distance stops being just a number and turns into a system-level hazard. People usually think of distance as emotional, far from home, far from rescue. But on a mission like this, distance is operational first. It affects everything. NASA treats distance from Earth as one of the major hazards of human spaceflight for a reason. It is not just about loneliness. It means no rapid resupply, no emergency evacuation, no replacement hardware arriving next month, no live expert team solving problems with you step by step, and no room for sloppy procedures. Every subsystem on the ship has to be treated like it will either be fixed by the crew or not fixed at all. That one fact changes mission design from the start. On a Neptune mission, every contingency has to be carried with you. Every spare filter, every backup pump, every extra circuit board, every surgical tool, every medicine, every diagnostic system, every emergency procedure. Support is no longer something waiting for you on Earth. It has to be converted into mass, power use, storage, redundancy and training before launch. And that makes the return problem worse, because everything you bring to survive the unexpected also becomes something you had to accelerate out to Neptune in the first place. That is why distance keeps pushing the mission toward failure, even if nothing dramatic happens. The farther you go, the more support stops being a capability and turns into a memory. At Neptune, there is no safety net under the mission. There is only the ship. Then the next problem gets even more serious. If the crew cannot depend on Earth in real time, what kind of crew do you even have to send? The answer is not just astronauts, at least not in the old sense. A Neptune crew would need full autonomy in medicine, engineering and navigation. Mars already pushes missions in that direction. Neptune completely removes the old model. The crew cannot wait half a day for Earth to tell them whether to reboot a damaged power bus, reconfigure atmosphere scrubbers, isolate a leaking line, or improvise a medical procedure. They have to decide, and they have to decide correctly while under pressure, with limited tools, inside a vehicle that has to keep working for years after the emergency ends. That means the crew has to carry the skills of an entire ground organization with them. Not just pilots, not just scientists. You need people who can act like doctors, surgeons, mechanics, electrical engineers, life support specialists, navigators, software troubleshooters, and mission planners. You also need overlapping competence because one person can get sick, injured, or die. So now the ship grows again, the training expands, the number of systems expands, the decision tree expands, and every time the mission grows more capable, it also grows heavier and harder to bring home. That is the part people usually skip. Autonomy sounds strong until you price it in hardware and mass. A crew that can survive without Earth needs more tools, more training, more backup systems, more onboard authority, and more onboard manufacturing or repair capability. In other words, a Neptune ship does not just carry people, it has to carry a portable version of the institutions that normally live on Earth. And the more complete that portable civilization becomes, the more punishing the return math gets. Then there is navigation, and this is where small errors stop being small. A trip to Neptune is not a straight highway. It is a long sequence of precise choices spread across years. Voyager 2 needed a carefully planned mid-course correction after Uranus to line up the Neptune encounter. That was for a robotic spacecraft on a flyby, with one clear target, guided by a team on Earth focused on one vehicle. A crewed mission would demand even tighter discipline over a much longer time. The ship has to stay on track for years, arrive correctly, manage insertion into one of the most distant major planetary systems we know, operate there, and still preserve enough margin to leave later. The problem is that light delay makes every navigation issue slower to detect and harder to reverse. If a trajectory drift is caught late, the fix costs propellant. If the fix costs too much propellant, then maybe you lose flexibility at arrival. Maybe you lose orbital options, maybe you lose the ability to descend near a target moon. Maybe you lose the departure margin that was supposed to bring the crew home. At Neptune, a navigation mistake is not just a line on a screen. It can quietly consume the exact resource that separated a difficult mission from a one-way mission. And because of the delay, support from Earth does not stop that in time. By the time ground teams analyze the problem, build recommendations, and send guidance back, the ship may already be deeper into the wrong path. That is what makes Neptune so dangerous operationally. Small mistakes have more time to grow before help can even enter the conversation. A minor error can age into permanent entrapment before Earth has finished answering the first message. That is the point where the title stops sounding dramatic and starts sounding technical. Never Come Back is no longer just about propulsion. It becomes a communication problem, a decision speed problem, a maintenance problem, and governance problem all at once. Once the crew reaches Neptune operations, Earth is no longer part of live action. Earth becomes delayed analysis, stored expertise, old procedures, and distant advice. The people on the ship are now the final authority, the repair team, the medical team, the navigation team, and the emergency team. That changes the psychology of the mission completely. They are not on an expedition with backup, they are the backup. and that matters for the return more than almost anything else. A return to Earth is not just something you do if the engines are good enough. It only happens if the crew makes the right decisions fast enough, fixes the right things early enough, preserves the right margins long enough, and avoids letting one local failure cascade into the loss of departure capability. If the habitat loses the ability to leave, Earth cannot talk it back into leaving. If the crew makes one wrong call during a crisis, Earth cannot rewind the timeline. If the ship starts drifting toward unrecoverable failure, the delay makes that drift harder to stop. So this is the second hard truth about Neptune. Distance does not only make the trip longer, it cuts the crew loose from live support and forces them to carry their own civilization inside the spacecraft. From that point on, every emergency is local, every bad decision is final, and every problem has hours to get worse before outside help can even join the discussion. And if light itself is already slow enough to break control, then the next problem is even more basic. How do you keep a ship alive at the edge of the solar system when the sun is barely useful anymore? The next thing that fails at Neptune is the sun. People usually treat sunlight as the default power source in space. Near Earth, that makes sense. Near Mars, it still mostly makes sense. By the time you get to Neptune, that logic is gone. Neptune is about 30 times farther from the sun than Earth is. That means the sunlight out there is not 30 times weaker. It is about 900 times weaker. That is what distance does to light. It falls off so hard that something which feels normal near Earth turns into a thin, weak energy source by the time you reach the outer solar system. The sun is still visible, but from an engineering point of view, it is barely helping you. It is not powering a serious human mission in any comfortable way. At Neptune, sunlight is no longer the backbone of the mission. It is barely part of the conversation. That changes everything immediately. In the inner solar system, solar power can feel cheap by comparison. You build panels, point them well, manage your loads, and keep going. At Neptune, power stops being cheap, passive, and easy to scale. It becomes something you have to fight for. And the more serious the mission becomes, the more obvious the answer gets. If you want to operate that far out, you need nuclear power. That is not speculation. That is exactly how serious outer planet missions are already designed. When NASA studies missions for the outer solar system, it does not act like solar power is the obvious foundation and nuclear is just a backup. It treats nuclear systems as the practical answer because sunlight has become too weak to carry the mission properly. Even the Voyagers depended on nuclear power sources to keep operating across deep space for decades. The Neptune Odyssey concept used 3 radioisotope generators, and that was for a robotic mission, not a crewed one. That point matters. If a robot needs nuclear power just to survive and do science at Neptune, then a human mission is not just going to need a little more. It is going to need much more. A crewed spacecraft would need power for the habitat, thermal control, life support, communications, water recovery, oxygen production, navigation systems, onboard computing, maintenance tools, medical equipment, internal lighting, backup systems, and emergency reserves. And none of that includes the extra demands that appear after years of wear, degradation, and contingency planning. So power at Neptune is not just one line item in the design. It becomes one of the main reasons the mission starts turning one way. Because as soon as your power system has to be that strong, that far from the sun, the ship starts getting heavier. And when the ship gets heavier, the launch problem gets worse, the propulsion problem gets worse. The return problem gets worse. The whole mission starts feeding on itself. Then there is another part people usually underestimate. Power is not just about running electronics. At Neptune, power is also heat. And heat is survival. A mission to Neptune is not just far, it is cold enough that keeping both humans and machines inside their safe operating limits becomes a non-stop job. Out there, every watt has multiple jobs at once. It has to keep the lights on, but it also has to keep the crew warm enough, the water system stable enough, the air system working properly, the instruments healthy, the seals flexible, the electronics responsive, and the structure from becoming harder to manage as temperatures stay brutally low. If you lose power margin, you do not just lose convenience, you start losing the conditions that make the spacecraft livable and repairable. That is why nuclear power in deep space is not just about electricity production. It is also about the heat it gives off. That extra heat can be the difference between hardware that stays functional and hardware that becomes sluggish, brittle, or dead. Near Earth, some thermal problems can be balanced in easier ways because the surrounding environment is less extreme and the energy supply is more forgiving. Near Neptune, the environment is already hostile by default. There is no easy version of thermal management there, and a return mission makes that burden even worse. It is not enough to keep the crew alive after arrival. You also need enough power left after all those years to support departure, support the return crews, and keep the spacecraft functioning all the way back into Earth space. That means the power system cannot just be adequate at Neptune. It has to still be adequate after a long outward journey, after years of exposure and decay, after wear in the habitat and life support loops, and after the stress of local operations. A ship that reaches Neptune but no longer has the power margin to leave safely has not completed the hard part. It has failed at the farthest point. And that leads to the next problem. In the inner solar system, you can sometimes manage a power shortage by scaling back operations, adjusting your orientation, delaying a non-critical task, or waiting for better sunlight conditions. At Neptune, that kind of flexibility is much weaker, because low energy is the baseline. It is not a temporary problem, it is the normal environment. That means the power system is not a supporting utility. It is the central organ of the entire mission. If it underperforms, everything starts degrading together. Communications become weaker, heating margins shrink, water recycling becomes harder to sustain, oxygen generation becomes harder to sustain, repair options narrow, internal conditions become less stable, even the crew's performance drops because people do not work well when the habitat feels fragile and every system is being throttled to preserve power. A shortfall at Neptune does not stay isolated, it spreads through the whole mission. That is what makes under-design so dangerous there. One weak power architecture can quietly turn a 2-decade expedition into a one-way drift. The ship may still exist, the crew may still be alive for a while, but if the power system no longer supports a healthy habitat and a departure-capable spacecraft, then the mission has already been pushed into failure whether anyone says it out loud or not. And once you follow that logic honestly, Neptune starts looking less like a difficult destination and more like a place that naturally becomes one way. If the environment is so hostile that even robotic exploration depends on nuclear-class power, then adding humans does not just raise the challenge a little, it causes the whole mission structure to swell. The propellant for the return wants bigger tanks. Bigger tanks want more mass support and stronger structure. More mass wants more launch energy and more capable propulsion. Bigger systems want more electrical power and more heat management. More power wants more nuclear hardware. More nuclear hardware wants more shielding, more structure, more redundancy and more maintenance support. Then all of that extra mass has to be carried outward across billions of kilometers before the crew even gets the chance to try leaving again. That is why go there and come back sounds simple in speech and starts collapsing in physics. The two legs are not equal. The outward leg is hard, but at least you start with a fresh ship, full reserves and a design built around reaching the target. The inward leg begins after years of degradation, after power losses, after system wear, after local operations, and after the ship has already spent the best part of its life just surviving the trip. You can sometimes force the outbound leg to work with enough investment. The return leg is where the numbers become much less forgiving. So this is the next hard truth about Neptune. The sun does not fully disappear, but it stops being a useful partner. Power becomes nuclear, limited, heavy and central to every other system. Heat becomes part of survival. Every watt has to do multiple jobs. And if the mission ever falls behind on power, the loss spreads through life support, communications, stability, and eventually the chance to leave. And once power becomes that hard to secure, the next problem gets even worse. Because reaching Neptune is difficult, but actually slowing down there and staying there is where the mission starts facing the full force of the physics. The hardest part of a Neptune mission is not getting there. It is slowing down when you finally arrive. People usually think deep space exploration is mostly about launch, speed and distance. With Neptune, that's only half the problem. A fast flyby is one thing, staying there is something else entirely. Voyager 2 proved that. It made it all the way to Neptune, but it did not stop. It flew through. That is why its best close-up science happened in a window of only a few hours. For a robotic mission, that can still be worth it. For a human mission, it is almost useless. You do not send people across the solar system just to race past the planet and disappear back into space. If humans go there, the ship has to brake, enter orbit, stay under control, keep enough flexibility for local operations, and still preserve enough margin to leave later. That means the spacecraft cannot just survive a long cruise, it has to arrive ready for the most demanding burn of the entire mission. That is where the mission becomes extremely fragile. After more than a decade in deep space, after years of system wear, power loss, maintenance and small failures, the ship reaches the Neptune system and suddenly has to perform a major braking event exactly right. If that burn fails, or underperforms, or happens at the wrong time, the crew does not start Neptune operations. They lose the mission at the point where everything depended on one event going correctly. That is the real danger of arrival. The mission can survive the long journey and still fail at the one moment that decides whether Neptune becomes a destination or a graveyard. And Neptune does not give you much room to improvise once you get there. This is not a small world with weak gravity and forgiving margins. Neptune is a giant planet. Its surface gravity, if you define it at the cloud tops, is a little stronger than Earth's, and its escape velocity is around 23.56 kilometers per second. Those numbers tell you something simple and important. Once you are deep in the Neptune system, every major maneuver happens in the presence of a strong gravity well. Slowing down costs energy, changing orbit costs energy, leaving later costs energy. Nothing about this is casual. That matters because people often think of arrival as the reward after the hard part. At Neptune, arrival is another hard part, and in some ways it is worse than the cruise. The ship reaches the farthest major planet, and instead of being done with the worst physics, it hits another major wall. To capture into orbit, you need propellant, precision, timing, and a spacecraft that still behaves like a healthy spacecraft. If you use too much propellant, you may protect the arrival but damage the return. If you arrive too fast, capture becomes harder. If you arrive with too little margin, every later decision becomes narrower. Neptune's gravity is strong enough that it punishes weak arrival planning immediately. And there is another problem hidden inside that. You cannot go a little lower into Neptune to help with the mission, because going into the atmosphere risks losing the vehicle. But if you stay too cautious and too high, you may lose access to the science targets, orbital options, or moon encounters that made the mission worth doing. There is no easy operating zone where everything becomes simple. Neptune is far enough away that reaching it already consumed years of time and huge amounts of mass, and then it is massive enough that capture and departure both still demand a huge amount of respect. That is why arrival at Neptune is not just a milestone. It is a second test of whether the whole mission architecture was real or only looked real on paper. So maybe the answer is gravity assists. Maybe you let Jupiter do some of the work, gain speed outward, shorten the trip, and reduce the burden. That helps, but it does not solve the real problem. Gravity assists are useful because they let a spacecraft trade momentum with a planet and reshape its path without carrying that extra energy entirely by itself. That is exactly why Jupiter shows up in real Neptune mission studies. Triton depended on a rare Earth-Jupiter alignment to get to Triton. Neptune Odyssey could also benefit from Jupiter to shorten cruise time. So yes, gravity assists matter. They can make the outward trip more practical. They can save years. They can lower some requirements. But they do not save you from Neptune. They help you reach the system. They do not remove the need to break into Neptune orbit. They do not keep a crew alive there. They do not preserve life support for years. They do not rebuild your margins after the ship ages, and they do not lift you back out later. That is the part people skip. A gravity assist can improve the outbound path, but it does nothing to erase the local physics when you finally arrive. Neptune still has to let you in, and later you still have to force your way back out with a ship that is older, more worn down, and carrying the consequences of every design compromise made at launch. That is why talking about gravity assists as if they solve the Neptune problem is misleading. They solve one slice of one leg, they do not solve the system. A human return mission still has to capture, operate, survive, preserve departure capability, and then execute another major propulsion campaign years later. Jupiter can help get you to the door. It cannot make the house easy to live in, and it definitely cannot guarantee that you can leave. Then look at the scale of what even a robotic Neptune mission already requires. Neptune Odyssey was not a tiny probe. It was a flagship-class orbiter paired with an atmospheric probe. The mass going to Neptune orbit was measured in tons, and the concept still depended on 3 radioisotope power systems. That matters because it gives you a reality check. If that is what it takes to send an uncrewed science package into Neptune orbit, then a human spacecraft is not just more of the same. It is a major jump into a much harder mission class. A crewed Neptune vehicle has to do everything that robotic orbiter does, but also keep people alive for years, provide pressure, heat, water recovery, air recycling, medical capability, radiation protection, maintenance tools, habitat volume, food storage, redundancy, and emergency response. Then after all that, it still has to leave again. That is the point where the return leg stops looking like an added feature and starts looking like the least believable part of the design. Because the return is not something you attach after a successful arrival. It demands another major propulsion effort after the ship has already gone through the hardest parts of the mission once. That is the real scale problem. A robotic Neptune orbiter is already a top-tier project. A human Neptune orbiter with return capability is not the next step after that. It is a cliff, and the cliff gets steeper because the second big propulsion campaign, the one that matters for getting home, happens when the spacecraft is oldest, the crew is most tired, and the mission has the least margin left. So the main point here is simple. At Neptune, the win is not getting there. The win is arriving there with enough ship left to matter. That completely changes how you should think about the mission. People naturally assume distance is the main challenge. Cross the billions of kilometers one, and the big job is done. Neptune flips that completely. Arrival is not the reward after the hard part. Arrival is the hard part in a new form, and any return plan has to survive that fact. It is not enough for the ship to reach Neptune. It has to reach Neptune with enough propellant still available, enough power still available, enough structural health still available, and a crew still functional enough to handle the next phase. It has to survive the braking event and still remain a departure-capable system. That is an enormous demand, because now the mission is asking the farthest major planet arrival humans have ever attempted to also be conservative enough to leave reserves for the trip home. That is where the idea of never come back stops being a dramatic line and starts turning into hard physics. A Neptune mission is not judged by whether it touches the system. It is judged by whether it can touch the system without spending the exact resources that were supposed to get the crew back. And the deeper you think about that, the worse it gets, because the next problem removes something even more basic than safe arrival. There is nowhere to land on Neptune in the normal sense at all. And that is the next problem. What does it even mean to land on a planet that has no surface? For most planets and moons, the word landing is simple. You go down, touch solid ground, stabilize the vehicle, and then decide what happens next. On Neptune, that whole idea stops working. Neptune does not have a solid surface you can stand on. There is no bedrock waiting under the clouds. There is no flat area where a ship can settle down. There is no base site, no runway, no stable platform, no place where you unload cargo and start planning a return. If you go to Neptune in the literal sense, you're not going down toward ground. You're going down into a deep atmosphere that keeps getting denser and stranger as you descend. That changes the mission immediately. The problem is no longer, how do we land safely? The problem becomes, how do we avoid getting trapped in a place that never turns into land at all? Because if there is no surface, then there is no normal way to stop, regroup, repair, refuel, or launch back out. A return mission depends on some kind of stable interface between the vehicle and the world it visits. Neptune does not give you that interface. And the name Ice Giant can make this sound less extreme than it really is. People hear that phrase and think of cold, maybe frozen layers, maybe some strange but still understandable version of a planet. But the word ice here does not mean frozen plains or a hard outer shell you can use. It is about chemistry. Neptune is made mostly of dense fluid forms of water, methane and ammonia, above a much smaller rocky core buried deep below. That core is not some accessible destination. It sits under conditions no human vehicle is going to descend through and then escape from. That is the key point. The more accurate your picture of Neptune becomes, the less the idea of landing survives. This is not a giant frozen world with a tricky atmosphere. It is a giant planet built from materials under extreme pressure and temperature conditions that do not turn into usable terrain for a crew. The deeper layers are not a backup landing zone. They are the reason no landing zone exists. So what happens if you keep going downward anyway? At the top, Neptune looks like what people expect from a giant planet. Clouds, winds, and an atmosphere made mostly of hydrogen and helium with some methane mixed in. But the farther down you go, the less it resembles the kind of environment spacecraft know how to visit and leave. Pressure rises, density rises. The materials stop behaving like the normal atmosphere people picture in their heads. The planet transitions into deeper fluid layers under conditions that become more and more hostile. There is no clean boundary where you can say, now we have reached the ground, there is only more planet. That is why the real scientific approach to Neptune's atmosphere is so revealing. When mission planners want direct data from Neptune, they do not talk about a reusable vehicle going down, collecting samples and coming back up. They talk about sending a probe into the atmosphere, letting it descend for a short time, gathering what it can, and then accepting that its useful life is basically over. One serious concept only planned for about 37 minutes of descent to reach the 10-bar level. And 10 bars is nowhere close to the bottom. It is just a scientifically useful depth. That alone tells you what kind of place this is. The serious architecture for entering Neptune is sacrificial, not recoverable, not crew-rated, not designed for return. That should remove any remaining comfort from the word landing. If the best way to directly study the atmosphere is to throw in a machine that is expected to die doing its job, then a crude descent and return plan is already disconnected from the way Neptune actually has to be approached. So maybe someone says, fine, then do not go deep. Just descend carefully, stay high enough, and keep the vehicle in a manageable layer. But that does not solve the problem either. There is still nowhere to stand, there is still nowhere to anchor, there is still no solid point where the mission becomes stable. The entire descent is just a path into worse conditions. Pressure gets higher, the environment gets denser. The vehicle has fewer good options, not more. And because there is no surface, there is no moment where the danger levels off and turns into something a return architecture can work with. That is why a crew that commits to descending into Neptune is giving up more than people realize. It is not just taking a risk. It is leaving behind the normal engineering logic that makes return possible. On the Moon, a lander can touch down, conserve fuel, and later launch from a known surface. On Mars, people can at least discuss habitats, ascent vehicles, and local operations on solid ground. On Neptune, there is no solid interface where any of that begins. You are descending into a gradient. And a gradient is not a place you can build a comeback from. That makes the whole idea brutally simple. There is no launch pad on Neptune. There is no safe parking spot. There is no repair site. There is no place to set up infrastructure for ascent. There is no calm layer where the vehicle can stop being a falling machine and start being a stable outpost. Neptune removes the category of footprint entirely. You do not arrive and establish a presence. You enter and keep sinking into a world that never gives you the one thing a return mission needs most: somewhere to be. And this is the first absolute barrier in the whole story. Long travel times are terrible, but you can at least imagine better propulsion helping with that. Communication delay is terrible, but you can imagine stronger autonomy helping with that. Power scarcity is terrible, but you can imagine bigger reactors helping with that. Arrival burns are brutal, but you can imagine more propellant and better guidance helping with that too. But no amount of improved shielding, better medicine, smarter software, or stronger engines changes the fact that Neptune does not offer a solid surface for a normal human return architecture. That is what makes this part so decisive. Up to now, most of the problems sounded like extreme engineering. Hard, but still in the category of engineering. This problem is more basic. It changes the shape of the mission itself. If you descend into Neptune, you're not choosing a dangerous place to land. You're choosing a destination that removes landing from the mission entirely. And once landing disappears, so does the normal logic of coming back. That is why the title starts sounding less dramatic and more direct here. Anyone who goes into Neptune is not heading for a difficult surface. They are entering a giant planet that gives them no obvious way to stop safely, no obvious way to operate stably, and no obvious way to leave. That is not a rough landing site. That is a one-way interface. And once that is clear, the next problem gets even worse. Because even before depth and pressure finish trapping you, Neptune's atmosphere itself starts acting like a place built to destroy the ship long before any return plan can begin. Now the problem gets more direct. It is not just that Neptune has no solid surface. It is that the atmosphere itself is not a place you can enter, study for a while, and then leave in any normal way. Once you go down into Neptune, you're not moving through air toward a destination. You're moving deeper into the planet. Start with what the atmosphere actually is. Neptune's atmosphere is mostly hydrogen and helium with a small amount of methane. The methane helps give Neptune its blue colour. But for a human mission, the important part is much simpler. This is not air you can work with. There is no oxygen in it for breathing. There is no familiar pressure range waiting below. There is no useful layer where you can say the environment has become manageable enough to treat like a difficult version of Earth. The atmosphere is not a thin skin covering a normal planet. The atmosphere is the outer part of the planet itself. That changes the whole idea of descent. People are used to thinking of atmospheres as something you pass through. You drop through air, you use it for braking, and eventually you reach the ground. On Neptune, there is no such payoff. You enter a giant planet atmosphere and stay inside the machinery of a giant world. There is no clear line where things become stable. There is no natural stopping point. There is no practical version of we will just skim a little lower and hover. The deeper you go, the more completely the atmosphere takes control of the mission. That is exactly why real mission concepts treat Neptune's atmosphere the way they do. When scientists want direct measurements from inside it, they do not plan for a reusable vehicle. They plan for an entry probe that goes down, gathers data during a short descent, and is effectively done after that. One serious concept for Neptune used an atmospheric probe that would descend for only about 37 minutes before reaching the 10-bar level. That number matters because it keeps this grounded. You do not need to exaggerate Neptune to make it sound impossible. The actual scientific plan is already telling you the truth. The way we study Neptune directly is by sending something into the atmosphere and accepting that its meaningful life is short. That should completely reset how people think about a human descent. If the correct robotic logic is send a probe in, get what data you can, and accept the loss, then a crewed descent and return mission is not just difficult. It is going against the way the environment itself has to be approached. Neptune is not a place where you send something down and expect to recover it later. It is a place where entry is already close to disposal. And the main reason is pressure. Giant planets can look soft from far away because they do not have a visible surface. That is a dangerous intuition. Neptune's upper clouds are not the real trap. The trap is what happens as depth increases. The deeper you go, the denser the atmosphere gets. The pressure rises. The thermal conditions change. The structure of the environment changes. And because there is no solid deck anywhere below, there is no moment when the spacecraft can stop descending and turn the situation into a stable operation. That is what makes Neptune so different from a hard landing on a rocky world. On a normal landing, altitude buys you time. You can slow down, adjust, maybe abort, maybe circle, maybe choose another site, and if you do land, you at least end up on something solid. In Neptune's atmosphere, altitude is just the amount of time you have left before the conditions get worse. Every meter downward is not progress towards safety. It is progress toward higher pressure, deeper entrapment, and fewer escape options. That matters structurally too. A vehicle descending into Neptune would not just be fighting drag or wind, it would be negotiating with a pressure environment that keeps getting stronger, while the vehicle has nowhere to stabilize. The craft has to survive changing density, turbulence, temperature shifts, and rising pressure without any safe pause point. There is no set down and inspect the damage phase. There is only continued descent into harsher conditions. The deeper you go, the less the mission can be recovered, because the environment is taking away both the ship's margin and the possibility of an organized departure. And Neptune adds another complication that makes the atmosphere even less passive. Neptune gives off more energy than it receives from the sun. That one fact explains a lot. It tells you this is not just a cold, quiet world sitting far out in darkness. The planet has internal energy contributing to what the atmosphere is doing. So when you look at Neptune's weather and its active atmosphere, you're not looking at something driven only by weak sunlight from very far away. You're looking at a planet whose interior is still feeding energy into the system. That makes the atmosphere harder to treat as a calm outer shell. It is not just cold gas sitting there waiting for you. It is part of an active planetary engine. The interior and atmosphere are exchanging energy, and that helps drive a more dynamic environment than people expect from such a distant world. So the crew would not only be dealing with remoteness and cold, they would be descending into an environment that is active from within, shaped by processes that are still not fully understood in simple operational terms. That is why Neptune's atmosphere cannot be treated like a hard but visitable place. Every important detail points the same way. The composition is wrong for human use. The atmosphere is deep enough that entry means entering the planet, not crossing a layer on the way to the planet. The Sirius probe concept is short-lived and expendable by design. Pressure gets worse continuously with no stable ground underneath. Internal heat helps keep the atmosphere active. None of those facts suggests a place where a crew can descend, do work, and then leave on schedule. And once you line those facts up, the conclusion becomes very simple. If you go down into Neptune, you're not going down to a place you can later launch from. You're not entering a difficult operating zone that becomes manageable with enough courage or enough engine power. You're entering a giant planetary environment that converts descent into loss. The return leg starts collapsing here. Before you even get to the later questions about weather, ascent, or long-term survival, because the atmosphere itself is already removing the normal conditions a comeback depends on. That is what makes Neptune so different from the worlds people usually picture in human exploration. On the Moon, the danger is exposure, but at least the ground is solid. On Mars, the atmosphere is thin and the environment is harsh, but at least there is a surface to work with. On Neptune, the atmosphere is not just one more hazard layered on top of the mission. It is the mission-ending environment itself. It is the place where the ship stops being a spacecraft on the way to somewhere and becomes an object being consumed by a giant planet. And if the atmosphere alone is already enough to remove the idea of safe descent and return, then the next problem makes that even harder to escape. Because Neptune's weather is not just bad, it is violent enough to make any human return architecture look unreasonable. Neptune's weather by itself is enough to break the idea of a human return mission. Even if you ignore the travel time, the communication delay, the power problem, and the fact that there is no surface, the weather still forces the same conclusion. This is not an atmosphere you pass through and manage. It is an atmosphere that keeps trying to take control of the mission away from you. Start with the basic number, because it is already bad enough on its own. Neptune has the fastest winds we know in the solar system. They can exceed 1,200 miles per hour, about 2,000 kilometers per hour. That is not a dramatic way of saying the planet is stormy. That is a measured fact. And once you say that number clearly, the engineering problem changes immediately. A vehicle descending into that atmosphere is not just dealing with weather as a background condition, it is dealing with one of the most violent large-scale fluid environments in the solar system. That matters because every atmospheric mission depends on one thing at some level: control. You need the vehicle to respond to guidance, to hold a planned path, to preserve structure, to manage heating, to protect propellant margins, and to keep the crew inside an environment that still behaves predictably. Neptune's winds attack all of that. A long-duration platform would not be designed for ordinary weather exposure. It would be designed for continuous conflict with the atmosphere itself, and that is already a bad sign. If the environment has to be fought every minute just to keep the vehicle usable, then the return architecture is already in trouble before the return even starts. Then look at the storms. People hear storm and picture a dangerous feature inside an otherwise understandable atmosphere. Neptune's storms are not like that. Voyager 2 saw the Great Dark Spot, a storm system about the size of Earth. Later observations showed that it disappeared, and other large storms formed elsewhere. That detail matters because it tells you something deeper than just Neptune has storms. It tells you the atmosphere is changing on its own terms. It can build giant structures, erase them, and reshape major features over time. That is bad for any human operation because stable systems need stable assumptions. A return mission needs predictable operating windows, predictable risks, and enough consistency to design around the environment instead of being surprised by it. Neptune does not really give you that. The storms are large, but the more serious problem is that the atmosphere does not stay fixed enough to make planning comfortable. A planet that can generate and remove Earth-sized storm structures is not giving you a calm operational background. It is reminding you that the atmosphere is active enough to keep changing the rules. And the strangest part is that this violence is happening in very weak sunlight. This is one of the most important things about Neptune because it breaks a lot of normal intuition. People tend to assume that strong weather needs strong sunlight. That makes sense on Earth. More solar heating usually means more energy driving the atmosphere. Neptune does not follow that simple logic. The planet gets very little sunlight compared with Earth, yet the atmosphere is still extremely active with very high winds and large storms. That means you cannot comfort yourself with the idea that distance from the sun must make the environment calmer. It does not. Neptune's weather is not just a thin outer response to sunlight. It is tied to the planet's deeper internal energy as well. So the low sunlight does not make the atmosphere gentle. It makes the whole situation stranger, because now you are dealing with a world that stays violent even in dim light. The edge of the solar system is not quiet just because it is dark. Neptune proves that clearly. That matters for the return argument because a crewed mission depends on more than survival. It depends on staging. It depends on having interfaces you can trust. It depends on being able to say this part of the environment is dangerous, but manageable enough to build around. Neptune's weather keeps weakening that hope. If the atmosphere is this active with so little sunlight, then the weather is not a temporary layer you wait out. It is part of the planet's identity. It is built into the world you're trying to operate in. So maybe orbit sounds like the answer again. Stay above the atmosphere. Avoid the descent. Keep the crew in a spacecraft around Neptune and let robotics deal with the lower layers. That does help, but it does not remove the weather from the mission. Any serious Neptune mission in orbit would still be shaped by what the atmosphere is doing below. Atmospheric probes depend on the conditions they enter. Remote sensing depends on cloud motion, storm activity, heat transport, and the changing structure of the atmosphere. Communications plans can be affected by how and where you operate near the planet. Low passes, science timing, orbital adjustments, and target priorities all become tied to a world below that refuses to stay quiet. So orbit does not erase the weather problem. It turns it into mission uncertainty instead of direct exposure. And that uncertainty is dangerous because Neptune missions already suffer from too many other constraints. The ship is already heavy, the power is already limited, the crew is already cut off from life support, the hardware is already old by the time it arrives, the return margin is already fragile, A changing, violent atmosphere below the spacecraft adds another layer of unpredictability to a mission that has almost no room left for surprises. Even if the crew never descends, they are still operating around a planet whose atmospheric instability shapes what they can do, when they can do it, and how much risk every action carries. That is why Neptune's weather is not just a side problem. It does not only threaten the fantasy of landing inside the atmosphere, it spreads outward and contaminates the entire idea that Neptune is a reasonable place for human operations that must eventually reverse direction and come home. A return architecture needs predictability, it needs controllable staging points, it needs places and phases where the mission can become more stable, not less stable. Neptune's weather gives you the opposite. It gives you motion, instability, and changing conditions on a giant planetary scale. And that is the feeling this section needs to leave behind. Not that Neptune is beautiful but extreme, not that it is dramatic, not even that it is only dangerous. The right word is unwelcome. Everything about the atmospheric environment tells you that humans are not supposed to do normal mission operations there. The winds are too fast, the storms are too large, the sunlight is too weak to explain the violence in any comforting way. The planet stays active anyway. There is no calm atmospheric space where a return vehicle can count on predictable conditions long enough to make a comeback plausible. So if anyone goes to Neptune in the literal atmospheric sense, they are not entering a harsh but workable environment. They are entering a planetary machine built around motion, pressure, and surprise, and those are exactly the things a return mission cannot afford. Then the next layer of the problem appears, and it is another one people do not expect. Neptune is not just distant, dark, and stormy. Even its magnetic field is wrong in ways that make the whole system harder to trust. Neptune has another problem that does not sound dramatic at first, but it becomes a real mission issue the moment you look closely at it. Its magnetic field is wrong in exactly the wrong ways. People usually picture a planet's magnetic field in a very simple way. You imagine something roughly centered, roughly aligned with the planet's rotation, with the most obvious effects near the poles. That mental model already fails at Neptune. Voyager 2 found that Neptune's magnetic field is tilted by about 47 degrees compared with the planet's rotation axis, and it is also offset from the planet's center. On top of that, the field is much stronger than Earth's. That combination matters because it means Neptune's magnetosphere is not neat, symmetrical, or easy to treat as a stable background condition. That changes the near-planet environment immediately. If the magnetic field is strongly tilted and offset then as Neptune rotates, the magnetosphere does not just sit there in one clean shape. Its geometry changes relative to space around it. The environment swings with the planet. So you are not dealing with a simple case where you map the magnetic field once, define the risky regions, and call it understood. The field arrangement itself creates a system that keeps changing with rotation. For a spacecraft, especially a crewed one, that means the space around Neptune is harder to simplify than people expect. This matters because human missions do not do well with environments that are both remote and hard to predict cleanly. A robotic probe can be built to tolerate a lot of uncertainty. A crewed vehicle has to worry about instruments, electronics, communication systems, power systems, habitat shielding, and long-term exposure patterns, all while preserving enough margin to leave later. A magnetic environment that keeps shifting in non-intuitive ways is not automatically fatal by itself, but it is one more thing working against stable planning. And Neptune is still surprising us even on this point. In 2025, Webb captured Neptune's auroras for the first time. That matters for more than the image itself. Those auroras showed up at geographic mid-latitudes instead of staying in the kind of neat polar pattern people instinctively expect from Earth. That is exactly the kind of detail that should make a human mission planner uncomfortable. It means the large-scale behavior of Neptune's magnetosphere still does not match the Earth-based intuition most people bring with them. That is the real significance of those auroras. It is not just that they look unusual. It is that decades after Voyager 2, Neptune is still revealing basic system behavior we had not directly seen. That is not what a mature, well-characterized destination looks like. A mature destination is one where the big environmental patterns are already familiar enough that mission designers can focus on operations. Neptune is still a place where even large-scale phenomena can still surprise us when new instruments finally look closely enough. That should change how you think about a human return mission. A round trip does not just need brute force, it needs environmental confidence. It needs enough understanding that the crew is not walking into a system where one more layer of weirdness keeps appearing after launch. Neptune keeps failing that test. 40 years after the only flyby, it is still teaching us basic things about how its space environment behaves. And this is where it is important not to exaggerate in the wrong direction. You do not need to say Neptune is the worst radiation environment in the solar system to make the point. The stronger and more honest point is that Neptune's magnetic field creates a charged particle environment that is less intuitive and less stable than a crewed mission would want. A highly tilted, offset field means the shape and orientation of the magnetosphere vary as the planet turns. NASA has described Neptune's magnetosphere as undergoing strong variations during each rotation because of that misalignment. For a mission, that means the field conditions and plasma conditions around the planet are not fixed in a clean way. And for spacecraft operations, that matters. It affects how you think about electronics exposure. It affects instrument design. It affects timing. It affects communications assumptions. It affects how conservative your habitat shielding needs to be. It affects how much confidence you can have that one orbit around Neptune behaves enough like the last one to count as routine. That kind of uncertainty is manageable in robotic exploration if the mission is designed carefully and accepted as high risk. For a human return mission, not fully intuitive and potentially variable is already a serious problem. Then Neptune adds another detail that makes this worse instead of better. The planet rotates quickly. A day on Neptune is only about 16.1 hours. That matters because it means the tilted magnetic geometry is cycling on sub-day timescales. The field configuration relative to surrounding space is not frozen long enough for people to pretend it is basically static during operations. It keeps moving. The environment around the planet changes as the planet turns. That is one more example of Neptune refusing to stay simple. A crewed mission there is already struggling with long travel time, very weak sunlight, nuclear power dependence, no surface, violent weather, and no real-time support from Earth. Now add a magnetosphere that is both strong and awkwardly arranged, and that keeps cycling fast enough to remain operationally annoying. It does not have to be the single worst feature of the mission to still matter. At Neptune, the danger comes from accumulation. One more complicated system is enough to make every other system harder. That is the bigger pattern now. Neptune keeps rejecting Earth, normal assumptions one after another. Its weather is not quiet just because the sunlight is weak. Its atmosphere is not something you pass through on the way to a surface. Its magnetic field is not centered and tidy. Its auroras do not appear where people first expect them. That is why this argument works best when you keep stacking real facts instead of trying to force a dramatic line. Neptune does not need one single perfect killer trait. It has a collection of medium to extreme traits, and almost all of them are badly matched to the kind of stability a human return mission needs. That is what makes the mission start looking less like exploration and more like surrender to physics. Distance is already pushing the crew away from live support. Power is already pushing the ship into heavy nuclear dependence. The atmosphere already removes the idea of landing. The weather already removes the idea of a controlled atmospheric operation. And now even the magnetic environment refuses to behave in a simple, Earth-like way. Neptune does not just challenge one part of the mission, it keeps making every layer of the mission less comfortable, less intuitive, and less recoverable. And then you get to the next problem, which sounds like a compromise until you examine it closely. Fine, do not descend into Neptune, stay in orbit, stay safe, study the planet from above. But orbiting Neptune does not solve the trap. It just changes what kind of trap it is. So maybe orbit sounds like the answer. Do not go into the atmosphere. Do not try to land on something that has no surface. Stay above the planet. Stay in a controlled spacecraft. Do the science from a distance and leave later. That is more realistic than descending into Neptune, but it still does not solve the return problem. It only changes the form of the trap. A crew in Neptune orbit still has all the main problems that were already breaking the mission before. The trip is still more than a decade long. The crew is still cut off from real-time help. Power is still limited and has to come mainly from nuclear systems. The magnetosphere is still strange. The hardware is still aging far from home. Thermal control is still a constant problem. Life support still has to keep working without rescue or resupply. And over all of that sits the same final requirement. The ship has to leave later. Orbit does not erase that. It only postpones the moment when the mission has to prove it was never one way. That is why orbit is not safety in the usual sense. It is only the least destructive way to remain close to Neptune. If the atmosphere is one kind of entrapment, orbit is another. It avoids immediate destruction, but it replaces it with long-duration dependence on a single spacecraft that has to keep functioning at the edge of the solar system while saving enough margin for departure. That is not a small improvement. It is just a slower version of the same danger. And even the orbital environment is not as clean as people assume. Neptune is not just a planet with empty space around it. Voyager 2 found rings there, and Neptune has at least 5 main rings along with prominent arcs. These are not simple, smooth bands that make the system easy to map and forget. Some parts are clumpy, broken into arc segments rather than forming a neat, complete ring. That matters because it means the space around Neptune is structured, dusty, and dynamically complicated in ways that mission planners have to respect. This is not about making the ring sound like a giant wall of debris. That would be the wrong way to explain it. The real point is more technical and more important. The presence of rings and arcs means you do not get to treat Neptune orbit like an empty parking zone. There are constraints. There are regions with more particles. There are orbital paths that are more complicated than just choosing any altitude and coasting. A human mission wants simplicity wherever it can get it. Neptune keeps taking that away. Even around the planet, the environment asks for caution, route discipline, and better knowledge than we currently have. Then there is Triton, and Triton makes the orbital problem harder in a different way. Once you are in the Neptune system, Triton is not just another moon off to the side. It is the main secondary target, a major scientific objective, and a major part of the system's orbital dynamics. Serious mission concepts built around Neptune do not ignore Triton. They use it. Repeated Triton flybys help shape the mission architecture. Gravity from Triton becomes part of how the tour is designed. That tells you something important. Neptune orbit is not a place where you casually park a crewed station and then leave whenever you feel ready. The whole system is more choreographed than that. Your path, your science operations, your fuel use, and even your later departure can become tied to moon encounters, orbital geometry, and timing decisions spread across months or years. That is manageable for a robotic mission, designed carefully around those rules. For a crewed mission that has already spent more than a decade getting there, it is one more layer of planning that can go wrong. And if your return burn depends on still having good control over all of that after decades in flight, then Neptune orbit stops sounding like a refuge. It starts sounding like a sequence you cannot afford to mismanage. The crew is not sitting in a safe zone waiting for a convenient moment to go home. They are living inside a system where geometry, fuel, target priorities, and spacecraft health all stay linked together. One bad decision or one badly timed problem can quietly damage the return without anyone noticing it immediately. Then there is the issue orbit never solves at all: human survival. Staying in orbit avoids the atmosphere, but it does nothing about the biological basics. A human orbiter still needs pressure control, oxygen generation, air cleanup, water recycling, waste handling, food storage, temperature control, medical care, and constant maintenance of the systems that make the spacecraft habitable. And this is not low Earth orbit where help is relatively near. This is Neptune. There is no quick resupply. There is no emergency return in a few days. There is no second ship waiting nearby. There is no hospital. There is no replacement crew. There is only the hardware you brought with you and the people already inside it. That matters because life support is not a one-time engineering achievement. It is a daily fight against wear, contamination, breakdown, and limited resources. Systems that are being developed and improved for Mars-class missions are already serious engineering challenges. Neptune is far beyond that. A crew living in orbit around Neptune would still be depending on a closed ecosystem of machines and stored supplies after a very long trip, during a mission phase with no rescue and no meaningful replenishment. Orbit buys you distance from the atmosphere. It does not buy you a supply chain or a second chance. And this is where Neptune becomes especially dangerous to the imagination, because it keeps offering versions of false comfort. Do not descend, just orbit. Do not depend on sunlight, just use nuclear power. Do not rely on life support, just train the crew more. Do not land on Neptune, maybe use Triton. Every time the planet seems to offer a manageable version of the mission, that version still comes with a wound that never heals. Orbit removes one category of danger, but it leaves the return leg weak. Nuclear power solves one problem, but makes the ship heavier and more complex. Triton looks like a backup option, but it creates new logistical burdens. Better crew autonomy helps with communication delay, but demands more systems, more training, and more onboard capability. That is the trick Neptune keeps playing on the mission. It never gives you a clean solution. It gives you compromises that look survivable for a moment and then turn out to be survivable only in a way that still threatens the return. Orbit around Neptune is exactly that kind of compromise. It looks like the safe version because the crew is not falling into the atmosphere. But the deeper truth is worse. Orbit is where Neptune looks survivable and quietly remains unrecoverable. That is why orbit is not the answer to the title. It is the more advanced version of the same trap. The crew is still too far away, the ship is still too old by arrival, the environment is still too demanding, and the departure still has to happen later with the same spacecraft that somehow survived all of it. Neptune keeps giving you one layer of manageability at a time, while keeping the overall mission hostile to return, and once that sinks in, the next step is unavoidable. Because even if the crew survives the trip, survives orbit, preserves life support, avoids the atmosphere and keeps the spacecraft functioning, they still have to do the one thing the entire mission has been quietly failing to guarantee from the beginning. They still have to leave Neptune again. And now you get to the part that quietly breaks the whole mission. Leaving Neptune again sounds like the natural second half of the plan. First you go there, then you come back, but once you look at the physics, the return is not the second half. It is the weakest promise in the entire mission. The same gravity that made arrival hard is still there when it is time to leave. Neptune is not a small world you can just push away from with a modest burn. Its escape velocity is about 23.56 kilometers per second. That does not mean a ship in orbit would need exactly that much change in speed to head for Earth, but it tells you the basic truth. This is a giant planet with a serious gravity well. Getting captured was hard. Getting out later is also hard, and now you're trying to do it with a spacecraft that has already been operating for years, far from help after the longest and most punishing part of the mission is already behind it. So what does that mean in practice? It means the propulsion system that brought you in has to still be healthy enough to support a major departure campaign years later, or the mission has to carry a second major propulsion architecture just for leaving. Both options are bad. If you depend on the same propulsion system twice, then that system has to survive a decade-plus cruise, the arrival burn, local operations, long-term storage, and then perform again when the crew's survival depends on it most. If you bring a separate departure system, then you have added more tanks, more engines, more plumbing, more structure, more failure points, and much more mass from day one. Either way, the return is already turning into a design penalty that starts on the launch pad. And that leads to the real tyrant of deep space mission design, return mass. People often think about the outward leg and the inward leg as if they are separate. They are not. The return makes the outbound mission heavier from the beginning. Every kilogram you want available for the trip home has to be pushed all the way out to Neptune first. That means return propellant, return tanks, return engines, return power support, return plumbing, extra spares for the systems that protect all of that, extra shielding, extra life support consumables, extra structure to hold it together, extra maintenance equipment to keep it usable. The return is not something you add later after arrival goes well. It is a weight penalty that haunts the mission from the first second of launch. That is what makes Neptune so brutal. A robotic Neptune orbiter is already a top-level mission. It already needs a long cruise, major power systems, and careful mass control just to get a machine there and keep it working. So when you add and then bring a crew back, you're not making a small upgrade. You're multiplying every burden. More return capability means more mass. More mass means more launch energy. More launch energy means more propulsion. More propulsion means more structure, more power, and more risk. The return plan is making the whole mission worse before the ship even leaves Earth. And then someone always reaches for the same escape hatch. Maybe you do not have to bring all the return propellant with you. Maybe you make it there, maybe you produce fuel locally. That idea works much better on paper than it does at Neptune. On Mars, at least the discussion makes sense. There is a surface. There is accessible carbon dioxide in the atmosphere. There is a clear idea of where equipment would sit and how industrial systems might run. It is still hard, but it is a real engineering conversation. Neptune does not give you that kind of foothold. There is no solid surface. There is no natural base site. There is no easy industrial interface. In the atmosphere, the conditions only get worse with depth. In orbit, you would still need infrastructure that does not exist and has never been demonstrated remotely at that scale. So the idea that you can just make the fuel there is not a real answer for a mission grounded in present-day reality. It is a placeholder for technology and infrastructure humanity does not have. Maybe very advanced future systems could one day try to harvest resources from giant planet environments, process them, store them, and support a crew doing all of that safely at Neptune distance. But that is not a Neptune mission anymore. That is a civilization-scale industrial system operating at the edge of the solar system. And if your return plan depends on that level of maturity, then right now it is not a return plan. It is wishful thinking. So if you cannot count on making the fuel there, then the comeback has to be brought from Earth, protected for years, and still be usable at the far end of the mission. That is where the next problem gets even worse, because the vehicle leaving Neptune would be the oldest and most stressed version of itself. This part matters because people picture departure as the start of the journey home, almost like the mission is finally relaxing. It is the opposite. The departure burn is not done by a fresh spacecraft. It is done by a spacecraft that has already spent roughly a decade or more in deep space. It has already endured the trip outward. It has already gone through radiation exposure, thermal cycling, component wear, power degradation, maintenance demands, and the strain of keeping human beings alive every day. Then it had to survive arrival. Then it had to survive Neptune operations. And now, after all of that, it is asked to perform one more major propulsion sequence that has to work almost perfectly. That changes the emotional logic of the whole mission. Return is not the reward after success. Return is the final test given to the oldest hardware at the farthest major planet. The ship has the least margin it will ever have. The crew is likely the most tired it will ever be. The systems have already been exposed to the longest list of stresses they will ever see. And that is the exact moment when the mission asked the spacecraft to prove it was never one way. That is a terrible place to hide your most important promise. Because if anything has quietly degraded beyond what the crew can repair, this is where it finally shows. A valve that aged badly, a tank that lost margin, a power bus that is no longer as reliable, a guidance component with reduced confidence, a life support chain that can still keep people alive but no longer supports a conservative departure window. None of these failures has to be dramatic to destroy the mission. At Neptune, small losses of confidence can add up until the crew realizes the ship is still good enough to survive in orbit for a while, but no longer trustworthy enough to commit to the burn that gets them home. And once you put all of this together, one way stops sounding exaggerated. The outward trip is already expensive and difficult. The arrival burn is already one of the most fragile parts of the mission. Going down into Neptune is not a real return path because there is nowhere to launch from. Staying in orbit avoids that, but still leaves you with a departure problem dominated by propellant, power, system age, and crew dependence on aging hardware. By the time you map all of that honestly, the return leg stops looking like a bold extra achievement and starts looking like the least believable part of the entire architecture. That is the moment the title really locks in. Not because people are weak, not because astronauts would not try, not because engineers lack imagination, but because Neptune turns return into the first claim you should distrust. It is the part of the mission that sounds normal in conversation and starts collapsing the moment you force it to live inside real mass budgets, real hardware lifetimes, real power limits, and real distance. And once people hear that, they immediately look for a workaround. Fine, maybe not Neptune itself. Maybe the smarter move is Triton. It has a surface, it is famous, it sounds like the backup plan. But Triton only looks like the answer until you understand what Triton actually is. So maybe Triton is the answer. That is the loophole almost everyone reaches for at this point. Neptune has no surface, so fine, do not go to Neptune itself. Go to Triton instead. It is solid, it is large, it is famous, it is one of the most interesting moons in the solar system. On paper, it sounds like the smart version of the mission. Then the real details show up, and that idea starts falling apart too. Triton is Neptune's largest moon, but it is not some calm, convenient backup base. It is probably a captured Kuiper Belt object. It is the only large moon in the solar system with a retrograde orbit, which means it goes around Neptune in the opposite direction from the planet's rotation. And it is one of the coldest known worlds, with surface temperatures around minus 235 degrees Celsius. That is the real starting point. The backup plan is not a friendly moon waiting to save the mission. It is an extreme outer solar system object captured by a giant planet and sitting in permanent deep freeze. That matters because the moment people hear moon with a surface, they start importing expectations from places like the moon or even Mars. A place to land, a place to build, a place to set up hardware and think more clearly about living there for a while. Triton does give you a surface, but that does not automatically turn it into a workable human destination. It just changes the problem. Instead of descending into a giant planet with no surface, now you are trying to survive on a frozen moon in one of the coldest, darkest and most remote planetary systems in the solar system. And Triton is not quiet in a comforting way either. Voyager 2 saw active geysers there with material rising more than 5 miles, around 8 kilometers above the surface. Scientifically, that is one of the reasons Triton matters so much. It is not dead. It is active. It has ongoing processes. Its surface is not just old, frozen rock sitting unchanged forever. But that should not make anyone think it is more welcoming. Activity does not mean easy operations. It means the world can still surprise you. That is the part people get wrong all the time in space exploration. They hear that a place is active and they instinctively hear interesting or even promising. Sometimes that is true for science. It is not always true for survival. On Triton, activity means the surface is still doing things you have to understand and plan around. The terrain is relatively young in places. Nitrogen is frozen on the surface. Plumes suggest internal or seasonal processes that are still shaping the world. That makes Triton a great target for robots and a very complicated place for humans. So now the safe alternative is starting to look much less safe. Yes, you can stand on Triton, but you are standing on a cryogenic world with an active surface in the Neptune system years from help, under conditions that still demand a very large amount of onboard independence. A world can be scientifically rich and logistically terrible at the same time. Triton is exactly that. Then there is the sunlight problem, and Triton does not fix that either. Triton reflects a lot of the sunlight that reaches it, because much of its nitrogen is condensed as frost. That can make it sound bright, at least visually. But visual brightness is not useful power. The sunlight arriving in the Neptune system is already extremely weak. Triton reflecting much of it changes how the surface looks more than it changes what the mission can do with it. So even on Triton, you do not escape the basic energy problem. You still need nuclear-class power if you want a serious human mission. You still have to keep people alive in extreme cold. You still have to keep machinery warm enough to function. You still need power for habitats, communications, life support, maintenance, and eventually departure. That means Triton is not a refuge from Neptune's main problems. It is Neptune's problems in a different form. You get a surface, but you keep the weak sunlight, the deep cold, the isolation, the delay, the dependence on nuclear systems, and the huge return challenge. And the cold here is not just very cold in the casual sense. It is not the kind of thing you solve with better clothing and stronger heaters. It shapes the whole mission. Materials behave differently. Machinery has to be protected constantly. Fluids, seals, electronics, moving parts, storage, surface operations, suit systems, and emergency response all become harder. The environment is not occasionally hostile. It is structurally hostile every hour of the mission. Then Triton adds one more problem that tells you how strange this system really is. Its orbit is retrograde. That is not just a small orbital detail for scientists to care about. It tells you Triton was almost certainly captured rather than forming around Neptune in the same orderly way many major moons formed around their planets. In other words, the main moon you want to use as a backup base is basically an interloper, a body taken by Neptune's gravity and locked into a backward orbit around a distant giant planet. That matters for the mission, because it tells you the Neptune system is not some simple, clean family of moons, where everything feels naturally arranged and operationally helpful. The biggest moon is dynamically unusual. The system is historically messy, and that helps explain why mission concepts there tend to involve complex tours and carefully designed flybys. Triton is not sitting inside a friendly local environment that simplifies planning. It is part of a distant, odd, and logistically awkward system where geometry matters and timing matters and nothing behaves in the easy way human exploration would prefer. So even on the operational level, Triton does not calm the mission down, it keeps it complicated. If your human mission depends on landing there, surviving there, operating there, and then launching away from there with enough capability left to escape Neptune's system and cross the solar system home, then the retrograde moon is not a neat solution. It is another layer of dynamical and logistical difficulty added on top of everything that was already wrong. That is why Triton does not rescue the title, it actually sharpens it. At first, Triton sounds like the answer people wanted. It has a surface, it has science value. It gives the mission somewhere solid to go, but when you look more closely, what do you really have? A captured outer solar system object, a moon with a backward orbit, a world near minus 235 degrees Celsius, a place with active geysers and frozen nitrogen, a place receiving extremely weak sunlight in a system that already forces you into nuclear power and long-term autonomy. A place that is still deep inside Neptune's gravity environment, still years from rescue, and still dependent on a return ship that somehow has to remain healthy enough to leave. So maybe you do not die by descending into Neptune. Fine, then you are living on one of the coldest worlds we know, still trapped in the Neptune system, still trying to solve the same return problem with even more surface logistics added on top. That is not a way out. It is just a more complicated version of being stuck. And that is why Triton matters so much in this story. It is the first serious workaround people think of, and it still fails to make the round trip believable. It gives you one thing the mission desperately wants, which is solid ground, but it does not remove the larger system that keeps turning return into the weakest part of the whole plan. Triton is not the happy ending. It is the place where the mission's best-looking escape route still leads back to the same conclusion. And once even Triton fails as the rescue idea, the remaining problems start stacking up fast. Because Neptune's system is full of smaller complications that do not sound fatal alone, but together they keep voting against any realistic way home. A mission to Neptune does not fail only because of the big obvious problems. It also fails because the whole system is full of smaller complications that keep stacking up until the mission runs out of clean options. That is how Neptune really defeats a return plan. Not always with one giant wall, sometimes with 100 smaller ones. Take the rings. Neptune's rings are not huge, bright structures like Saturn's. They are faint, dusty, clumpy, and broken into arcs in places, and that's exactly why they matter. Big, obvious hazards are easier to respect. You see them, map them, and stay away. A messy, structured ring environment is harder in a quieter way. It means the space around the planet is not just open room where a crewed vehicle can park anywhere and relax. It means navigation has more rules. It means some paths are cleaner than others. It means the confidence you want in orbital operation starts getting chipped away by particle populations, ring arcs, and the fact that the system is less simple than you hoped. That is how real missions get harder. Not because there is a giant movie-style debris wall waiting to destroy the ship, but because a dusty and structured environment forces caution into every decision. Flight corridors get narrower, operational freedom shrinks, shielding assumptions get more conservative, timing gets stricter, simplicity disappears. Neptune does not need one dramatic ring hazard to create trouble. It only needs enough local complexity to make every orbital choice less comfortable than it looked from far away. Then there is the bigger problem behind that. We still do not know Neptune well enough to feel relaxed about any of this. That should matter much more than people think. Voyager 2 discovered multiple moons during a single flyby. That alone tells you how incomplete our picture was. Then decades later, Hubble kept adding more context. Webb added more context. Neptune's storms have changed. Its auroras were only directly captured recently. Even the planet's public-facing colour had to be updated after better image processing showed it looks more like Uranus than many people thought. That may sound like a side detail, but it points to something important. Neptune is still a place where basic context is being corrected and improved. It is not a finished destination. It is still an active frontier of discovery. That matters because a human return mission depends on mature knowledge. You want the environment to be boring by the time you send people. You want the big surprises gone. You want the main unknowns mapped out, tested and narrowed down by repeated robotic missions. Neptune does not give you that yet. It still keeps showing us new layers of itself with each improvement in observation. That is exciting for science, but it is bad for logistics. A place that is still teaching us basic things about its behaviour is not a place where you should feel comfortable building a round-trip human architecture, and distance makes that uncertainty much more dangerous. Closer to Earth, ambiguity is easier to manage. If something is not understood well enough, you can launch another mission sooner. You can update hardware. You can learn from one flight and apply it quickly to the next one. You can send replacement parts. You can change procedures fast. Low Earth orbit and even nearer deep space operations benefit from that learning cycle. Neptune does not. At Neptune, uncertainty ages badly. If your models of the rings are a little off, that matters more because you cannot easily send a second support mission. If your understanding of the magnetic environment is incomplete, that matters more because the crew cannot just wait for a quick upgrade from Earth. If your assumptions about atmospheric behaviour, Triton conditions or long-term hardware wear turn out to be too optimistic, you do not get a fast correction. You get a crew already committed to the mission, already years from help, already dependent on a vehicle that has to survive all the consequences of those wrong assumptions. That is why Neptune is such a hard place to extrapolate into a human round trip. Sparse reconnaissance is one thing if the mission is robotic and built to accept high uncertainty. It is something else if the mission contains people who have to come home. Unknowns that feel manageable in robotic science can become serious threats in crewed mission design. The farther from Earth you go, the less tolerance you have for being even slightly wrong. Then look at what the real science community is actually asking for. That tells you a lot. When people get serious about Neptune, they do not begin with crew cabins, surface bases, or return vehicles. They start with robotic missions, orbiters, atmospheric probes, carefully designed flybys of Triton. That is not because the scientists lack ambition, it is because they understand the stage we are in. And that stage is still reconnaissance. The smart move at Neptune right now is not to rush humans there. It is to send better robots and get better data, learn the system, map the hazards, improve the models, understand the rings better, understand the atmosphere better, understand Triton better, understand the magnetic environment better. That is what serious mission studies are saying by the choices they make. They are not acting like Neptune is one engineering push away from becoming a human destination. They are acting like it is still a place that needs to be studied carefully before anybody even starts pretending a round trip makes sense. That is one of the strongest points in this whole argument because it keeps the conclusion grounded. This is not fear talking, it is behaviour. The people closest to the science are still asking for better reconnaissance, not human logistics. That tells you Neptune is not in the commute era. It is not even in the rehearsal era. It is still in the era where the right response is to learn more before making bigger promises. And once you put all of this together, the pattern becomes very clear. Neptune is not blocked by one giant locked door. It is blocked by a whole stack of smaller doors, and every one of them is hard enough to matter. Distance matters, weak sunlight matters, communication delay matters, orbit insertion matters, no surface matters, atmospheric violence matters, magnetic weirdness matters, ring structure matters, Triton's cold matters, limited reconnaissance matters. None of these has to be the single perfect reason on its own. The problem is that they all point in the same direction. They all make return less believable. They all demand more mass, more caution, more power, more knowledge, more redundancy, and more luck. That is what makes the title feel earned instead of exaggerated. A one-way destination is often not a place with one unbeatable feature. It is a place where the whole environment keeps voting against your comeback plan till there is no believable path left. Neptune keeps doing that. It keeps taking every possible version of the mission and loading it with one more complication, one more uncertainty, one more system that has to work better and longer than any real human mission has ever had to work before. And then that raises the next problem, which may be the most brutal one yet. Because even if you somehow solve the distance, the power, the orbit, the rings, the atmosphere, Triton, and the communication delay, the ship still has to survive the thing Neptune quietly weaponizes against everything else: time. The next problem is not one dramatic failure. It is aging. A Neptune return ship would be getting older for years before the most important part of the mission even starts. And that matters because this vehicle is not doing one job. It is doing a whole list of jobs that normally get separated across different systems, different missions, and different support networks. It has to launch from Earth. It has to survive deep space for more than a decade. It has to act as a habitat the entire time. It has to handle medical problems. It has to support repairs. It has to produce or manage power for years. It has to communicate across billions of kilometers. It has to shield the crew from radiation as much as possible. Then it has to arrive at Neptune and still work as an operations platform. Then years later it has to become a departure vehicle and take everybody home. That is a huge demand even before you look at the actual subsystems. Human life support alone already requires a lot. You need stable pressure, oxygen control, air circulation, carbon dioxide removal, water recovery, waste handling, temperature management. All of those systems already matter in missions much closer to Earth. Stretch that out to Neptune and the problem changes completely. You are no longer asking whether the ship can do these things for months or maybe a few years with strong support from home. You are asking whether it can keep doing them across timescales that no human deep space system has ever demonstrated. That is the first part people underestimate. A Neptune return vehicle is not just a bigger spacecraft. It is several mission categories glued together and forced to stay trustworthy for far longer than any crewed deep space system has ever been asked to stay trustworthy. If even one major category starts degrading too far, the return starts falling apart long before the crew officially gives up on it. And yes, we do have a famous example of spacecraft lasting a very long time in deep space. Voyager has been operating for more than 47 years. That is one of the great engineering achievements in human history. But it proves the wrong lesson for a human Neptune mission. Voyager is a robot. It does not need a breathable atmosphere inside it. It does not need a water cycle. It does not need surgery. It does not need sanitation. It does not need sleep space, food systems, temperature comfort, or daily maintenance of a small artificial ecosystem. It is minimalist, remotely managed, and designed to keep doing useful work even as parts of it slowly shut down. That is exactly why it can survive for so long. A human mission is almost the opposite of that. A human Neptune ship would be packed with closed-loop systems, habitat systems, crew interfaces, safety layers, medical equipment, repair tools, storage systems, and all the daily machinery required to keep human biology from falling apart. The tolerances are tighter. The acceptable failure rate is much lower. The demands are much higher. A spacecraft that can keep a radio and a few science instruments alive for decades is not the same thing as a spacecraft that can keep a group of people alive, healthy enough and operationally sharp enough to leave Neptune and come home years later. That difference is everything. Robots can survive by degrading. Humans usually cannot. A robotic mission can keep producing value even after losing systems. A human mission reaches a point where enough small losses suddenly make the habitat unsafe, the crew less capable, or the return too risky to attempt. So when people point to deep space robotic longevity as proof that a Neptune-crewed mission is just a matter of scale, they are missing the central issue. The hard part is not keeping a machine alive. The hard part is keeping a living environment alive, and that brings you to life support, which is impressive, but still nowhere near magical enough to erase this problem. Closed-loop systems have made huge progress. Water recovery has improved, air revitalization has improved, recycling has improved. That is real progress, and it matters for any future deep space mission. But progress is not the same thing as completion. These systems still have to be monitored, repaired, cleaned, protected, and occasionally replaced. They still depend on pumps, filters, scrubbers, separators, sensors, seals, software and control electronics. They still need spare parts. They still need stored consumables as backup. They still need waste to be handled safely. They still need human attention every day. None of that disappears just because the recycling percentage gets better. And on a Neptune mission, every one of those parts becomes part of the return problem. A failed scrubber is not just a maintenance event. A degraded pump is not just an inconvenience. A water recovery problem is not just something you schedule around until the next cargo vehicle arrives. There is no next cargo vehicle. There is no nearby station. There is no fast rescue. If enough of those systems start failing or losing efficiency, the crew is not waiting for help. They are simply trapped inside a ship that is becoming less able to sustain a safe departure. That is what distance does to maintenance. It turns routine wear into mission-ending risk. A shortfall that might be recoverable closer to Earth becomes a geographic sentence at Neptune. You are not delayed until assistance comes. You are stuck with the consequences of whatever the ship can no longer do, and the ship would have to be tested to a level that is very hard to feel comfortable about. Extreme hardware testing is already a major part of spacecraft development. Systems get tested in vacuum chambers, under thermal stress, and through all kinds of environmental simulations because space destroys hardware in slow and relentless ways. That matters even more at Neptune distance, because a return-capable ship would need confidence not just across one long trip, but across two major interplanetary legs separated by the most demanding operations of the entire mission. That is a frightening requirement when you say it clearly. You're not testing whether the spacecraft can survive launch and one cruise. You're testing whether it can launch, cruise outward for years, arrive, operate in the Neptune system, preserve enough capability, and then still perform the departure and survive the return. That is a different level of confidence entirely. There is no historical database deep enough to make that feel routine. No crewed spacecraft has ever done anything close to that in deep space. The test program would have to justify trust in a vehicle that will become the most used, most stressed, and most aged human spacecraft ever built by the time it reaches the phase where failure matters most. And that phase is the return, not the launch, not the cruise, and not even the arrival. The return. That is the moment when the ship has the least margin left and is being asked to do one of its hardest jobs. That is why the spacecraft itself becomes a reason the crew may never come back. Not because one giant explosion has to happen, not because the mission needs a single dramatic disaster. The more realistic danger is slower than that. Time keeps eroding certainty. Bearings age, seals age, wiring ages, electronics age, tanks age, valves age, software assumptions age, materials age, the crew ages too, their health changes, their stress accumulates, their ability to repair, improvise, and stay sharp is being tested across a timescale no human mission has ever proven, even the mission plan ages, because assumptions that looked conservative at launch may not still look conservative after years of wear and unexpected deviations. That is what Neptune does better than almost any other destination in the solar system. It weaponizes duration. It takes every system that might have been manageable on a shorter mission and makes it older by the time it matters most. A component that would be acceptable for a Mars mission may not be acceptable for Neptune simply because Neptune gives it so much more time to drift, wear out, or surprise you. A crew that could handle one major mission phase may not be the same crew after surviving many years of confinement, stress, maintenance, and decision fatigue. A return plan that looked plausible at departure from Earth may look much weaker at Neptune simply because the hardware and humans carrying it are no longer the fresh versions of themselves. That is why this problem is so serious. It is not one failure mode. It is all failure modes stretching out over time until enough of them start overlapping. A Neptune mission does not need a villain in the usual sense. The mission can fail because nothing spectacular happened and too many ordinary things kept getting older. And that is the hardest part to hear if you still want the round trip to work. The ship that leaves Neptune, if it ever leaves, would not be a heroic fresh machine beginning a clean run home. It would be an old spacecraft carrying old decisions, old repairs, old compromises, old scars, and a crew that has spent years holding the whole thing together. It would be the most experienced object humans have ever flown, but also the most exhausted. And that is exactly when it would need to perform its cleanest, most unforgiving maneuver, the one that gets everyone home. So Neptune is not just distant in space, it is distant enough in time to turn the spacecraft itself into part of the trap. And once that becomes clear, the next problem becomes even harder to ignore, because the hardware is not the only thing aging out there. The human body is aging too. The next limit is not the ship, it is the crew. People like to talk about deep space as if the body will somehow adjust if the mission is important enough. But the human body is not rated for the version of Neptune people want to believe in. NASA is very clear about the main hazards of human spaceflight: radiation, isolation and confinement, distance from Earth, gravity or the lack of it, and closed or hostile environments. A Neptune mission takes every one of those hazards and pushes them much farther than anything humans have actually done. Radiation gets worse once you are far beyond Earth's protection. Isolation stops being a tough season of life and starts becoming the condition of the mission. Distance removes rescue as a real option. Long exposure to low gravity or weightlessness keeps wearing down muscles, bones, the cardiovascular system, and basic physical conditioning. And the closed environment of the spacecraft stops being the setting and becomes the entire biological support system keeping the crew alive. That is what makes Neptune different. On shorter missions, these hazards are serious, but they compete with each other inside a limited timeline. At Neptune, they start working together. The crew is not just exposed to one problem at a time, they are aging inside all of them at once for years, while depending on the same ship to keep them functional enough to eventually leave. That is not a small extension of human spaceflight. It is a demand for a level of biological endurance we have not demonstrated. Then look at the gap between real human spaceflight history and the kind of timeline Neptune would demand. The single mission endurance record that people still point to is 437 days. That is an extraordinary achievement. But it also reveals how far away Neptune still is from proven human capability. Some Neptune mission concepts need around 12 to 16 years just for the outward cruise. Just the outward cruise. That means even before local operations and the return leg, The mission has already gone far beyond the longest single human spaceflight mission by a huge margin. That does not mean humans cannot survive long missions at all. That is not the point. The point is that a Neptune return mission is not a stretch beyond our experience. It is a jump far outside it. We do not have a human evidence base for people staying operationally sharp, medically stable, and mission capable across that kind of deep space timeline. The mission is asking for years of performance in an environment where our proven record is measured on a much smaller scale. That is not just a gap in technology, it is a gap in biological confidence. And then there is radiation, which gets much worse once Earth is no longer protecting you. In low Earth orbit, astronauts still benefit from being relatively close to Earth's magnetic shielding. A Neptune mission does not get that protection for a few days or weeks. It gives it up for years. Radiation stops being a background concern and becomes part of the architecture of the mission. It affects cancer risk. It affects the nervous system. It affects long-term health in ways that are not fully comfortable even for shorter missions. It also includes the threat of sudden events like solar particle storms that can deliver dangerous doses quickly if the ship is not prepared. That is why shielding becomes such a hard trade. The crew needs shielding because the trip is long and the environment is unforgiving. But shielding is heavy, and heavy means more mass, more launch energy, more propulsion burden, and more pressure on the return plan. This is one of Neptune's ugliest patterns. The things that help the crew survive also make the mission harder to bring home. If you add more shielding, the ship gets heavier. If you keep the ship lighter, the crew lives with more radiation exposure. There is no clean answer there. Neptune keeps forcing the same choice again and again. Protect the crew more and damage the mission margins, or protect the mission margins more and accept worse biological risk. Then there is the psychological side, and this is not a soft problem. At Neptune distances, psychology becomes part of the engineering. A crew that is isolated for years, confined inside the same habitat, cut off by hours of communication delay, and living under constant system dependence is not just dealing with stress in the ordinary sense. They are dealing with conditions that can shape judgment, patience, conflict, motivation, and decision quality over very long periods. That matters because a psychologically degraded crew does not only feel worse, it performs worse, it notices subtle hardware problems later. It communicates worse with each other. It diagnoses failures worse, it responds to emergencies worse. It executes critical burns with less clarity. It makes maintenance errors more easily. That is why the mental state of the crew is not separate from the return problem. At Neptune, it is part of the return problem. Coming home depends on the crew staying competent, coordinated, and resilient across the longest and most isolated mission humans have ever attempted, and the timing makes that especially dangerous. The return leg would begin when the crew is the most tired, the most isolated, and the most worn down by the mission. That is the exact moment when the ship also needs them at their best. It needs them to make good decisions, preserve procedure discipline, and handle one final phase of high-risk operations with very little margin for mistakes. So psychology is not just about morale. It is about whether the people on board still function like the kind of crew that can get a fragile spacecraft home from the edge of the solar system. Then go back to the body more generally. Long missions in low gravity or weightlessness do not just create vague health concerns. They slowly wear down the systems a crew depends on. Muscles weaken, bone density drops, the cardiovascular system changes, balance and coordination can be affected. Recovery from injury or illness becomes harder in a closed spacecraft far from care. Medical problems that might be manageable on Earth or in nearer space become much harder when the crew has limited equipment, limited medicine, delayed contact with experts, and no evacuation option at all. That is the part people often ignore when they talk about brave astronauts going the distance. Bravery does not rebuild bone. Bravery does not stop radiation. Bravery does not replace medical infrastructure. Bravery does not make a body perform like fresh hardware after years of confinement and stress. A Neptune mission asks the human body to stay good enough for long enough under conditions where almost every known major hazard of spaceflight is turned up. So the fair conclusion is not that the body would instantly fail. that would be the wrong way to say it. The stronger and more honest conclusion is that a Neptune mission asks too much from too many human systems at once for too long, beyond what we have actually demonstrated. We already know long-duration spaceflight is hard. We already know radiation is serious. We already know life support is demanding. We already know isolation changes human performance. We already know distance from Earth removes rescue and fast medical help. None of those facts points toward a comfortable or credible round trip to Neptune with present-era realism. They point the other way. They point toward the same conclusion the engineering keeps pointing toward. If someone goes to Neptune under anything close to present-day constraints, the odds of Earth ever seeing them again do not collapse only because of rockets or fuel or distance. They collapse under biology too. The ship has to survive, but the crew has to survive in a useful state as well. And Neptune makes both those demands at the same time for far too long. That is why this mission keeps failing from every angle. Distance hurts the systems, time hurts the hardware, radiation hurts the crew, isolation hurts performance, low gravity hurts the body. The closed habitat becomes a permanent dependency. Every category feeds into the next. And that leads directly to the final point. Because Neptune's real power is not any one of these problems by itself. It is the way all of them merge into one problem. The real reason no one comes back from Neptune is simple once you see it clearly. Every problem turns into the same problem. Distance is not just distance. Distance makes communication slow. Slow communication forces autonomy. Autonomy needs more training, more tools, more onboard expertise, and more backup systems. More backup systems mean more mass. More mass means more propulsion. More propulsion means more tanks, more structure, more power demand, and a harder return. Power is not just power. Power affects heat, life support, communications, maintenance, and whether the crew can keep functioning at all. Life support is not just life support. It depends on power, spare parts, crew health, repairability, and time. Crew health is not separate either. If the crew gets weaker, more stressed, more isolated, or less sharp, then maintenance gets worse, decisions get worse, navigation gets worse, and the return gets worse. At Neptune, nothing stays in its own category. Every part of the mission leaks into every other part until the whole thing behaves like one giant system with no easy fix anywhere inside it. That is why the title works. Neptune does not beat you with one perfect killer feature. It beats you by making everything matter at once. If the trip were only long, maybe better propulsion would help. If the problem were only power, maybe bigger reactors would help. If the problem were only communication delay, maybe better autonomy would help. If the problem were only biology, maybe better medicine would help. But Neptune does not give you the kindness of one clean problem. It gives you all of them, and every attempt to solve one pushes on the others. That is also why the easy escape routes keep disappearing as soon as you test them against the real planet. You cannot land in the normal sense because there is no solid surface. You cannot trust sunlight because the Neptune system gets only a tiny fraction of the solar energy Earth gets. You cannot rely on mission control because messages take hours, not seconds or minutes. You cannot treat the atmosphere like a hard but manageable layer because the winds are extreme, the pressure gets worse continuously, and the planet gives off more energy than it gets from the sun. You cannot move the whole idea over to Triton and act like the problem is solved, because Triton is still one of the coldest known worlds on a retrograde orbit, with active geysers, weak sunlight, and the same huge return distance still waiting after you land. That is the trap. Every workaround sounds reasonable from far away. Then you add the real conditions, and it just stops being a workaround. It just becomes a new version of the same mission failure. Stay in orbit instead of descending. Fine. Then you are trapped by aging hardware, life support limits, power scarcity, and the need to leave later. Go to Triton instead of Neptune. Fine. Then you're trapped on a frozen moon in the Neptune system with the same nuclear power problem and the same impossible return demand. Bring more shielding. Fine. Then the ship gets heavier. Bring more propellant. Fine. Then the launch gets harder. Bring more crew expertise. Fine. Then the ship gets more complex. Neptune keeps taking every solution and attaching a new cost to it until the return leg becomes the least believable promise in the entire mission. And our own behaviour already shows that we know this. Look at the missions people seriously propose to Neptune. They are not crude ships, they are robotic flybys, robotic orbiters, robotic atmospheric probes, and carefully designed Triton encounters. They are nuclear-powered, long-duration, high-commitment machines built to gather data where humans cannot yet go safely. That is not a lack of ambition. That is ambition staying inside the laws of physics. The fact that the best real Neptune plans are still uncrewed is not some temporary embarrassment waiting for better PR. It is the clearest answer you could ask for. We are still trying to understand Neptune well enough to send better robots. That is the stage we are in. We are not even close to the stage where a human crew can expect a credible round trip. That point matters because it keeps this conclusion honest. This is not about saying never in some absolute science fiction sense. Never here means not with any mission architecture grounded in present-day demonstrated capability and the actual Neptune system we have observed. Could a much more advanced civilization change that someday? Maybe. If you had radically better propulsion, much more mature closed-loop biology, autonomous medicine that can handle major emergencies far from Earth, industrial infrastructure spread across space and nuclear systems at a completely different scale, then maybe Neptune stops being a one-way destination. But that is not the mission being discussed here. The real question is Neptune as it exists, and humanity as it exists, and when you put those two things together, the answer stops being mysterious. Voyager 2, Hubble, Webb, NASA mission studies, JPL, orbital dynamics, human spaceflight medicine, life support reality, radiation risk, communication delay, power limits, long-duration system aging, all of it points the same way. If you send people to Neptune now in any literal sense that matters, you're not sending them on an expedition with a hard return. You're sending them away and hoping the words "return mission" survive longer than the math does. That is the final escalation in the whole story. Neptune does not kill the dream of exploration. It changes the price until the dream stops fitting inside the civilization we have. The moon still feels near. Mars still feels like a frontier humanity could realistically push into. Even Saturn can still survive in the imagination as a distant goal. But Neptune is where the solar system stops behaving like a place humans can simply choose to visit and then come home from. It is where exploration starts demanding not just courage, not just engineering, not just money, but a whole different level of power, manufacturing, medicine, autonomy, and time. That is the real reason no one who goes to Neptune comes back. Not because Neptune is only far, not because one storm or one burn or one system kills the mission by itself. The reason is that Neptune is where all the unfinished parts of human spaceflight stop being manageable and start becoming fatal together. The ship is not ready for that timeline. The crew is not proven for that timeline. The power systems are not comfortable at that distance. The rescue model disappears. The landing model disappears. The easy backup plans disappear. And when every unfinished part of human spaceflight shows up in one mission at the same time, the return promise is the first thing that breaks. So if someone goes to Neptune now, the hardest truth is also the simplest one. They are not going on the longest trip humanity has ever taken. They are going on the first trip where the solar system finally says no. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.